21. Let me share my screen. My screen is visible. Okay. Total 22. Let's wait for 2-3 minutes. Then we'll start. Sheet 3. Hope no issue with this diagram till now. Discuss this. Then we'll went to stress strain diagram. Then we have seen the different parts of this curve. Then we'll move to the strength properties. Okay, these are the strength properties we'll discuss, and then we'll do a problem based on this curve. Okay, 25. Where are others? Please put a message in the group that class will start, because I haven't put a message in the group. So they might don't know that I'll start the class now. CR is there, so please, if CR is there or anyone can put a message in the group, please put a message that ma'am asked to join all of you, so that I can start the class. 30. Perfect. I hope I can start the class now because it's already 10:22. Okay, so let's start the class. So this in the last class we have discussed about this stress strain graph. Okay, now we'll discuss the material properties associated with this stress strain diagram we have developed. Okay, now we are going to define something called Hooke's law. Okay, so here is a normal stress strain curve for a ductile material or typical ductile material. Suppose that we came up. So with the stress strain diagram, we can start at we can start to look at material properties. So stress strain diagram is a key factor in determining the material properties. Let me note. Okay. So and the first property we are going to look at is what we call stiffness. Okay, we'll call this as stiffness, and that's in a linear elastic region. The stiffness is depicted in only in linear elastic region. We said that the slope of this line in this linear elastic region as E. We represented the slope of this curve as E, which is also called as Young's modulus or modulus of elasticity, and it is used in what's called Hooke's law. Okay, which is valid for the linear elastic region where the stress is equals to the Young's modulus times the strain. Stress is equals to the Young's modulus times the strain, and Hooke's law was named after British physicist Robert Hooke, but actually believed the concept was it was believed by Leonard Euler. Okay, but the stiffness, the slope okay, for this, if the slope becomes higher, if E value is higher, then your material is more stiff, and if the and the greater as the material is more and more stiffer, that means if the slope becomes greater, if the slope of this curve is greater, then it will be more and more steep, and then it goes downward. Suppose you have curve like this, so you will get lower steep. If the curve is like this, so you will have more E value, more slope. So more the we can say more the slope, more will be the stiffer element. More the E value, more will be its stiffness. Less E, if E is more, it will be more stiffness. Okay, and if E is less, it will be less stiffness. Okay, let me remove this part. I not want. Hope this part is clear. Stiffness. More the E value, more the slope of this curve, more will be the stiffness. Less the less the slope, then it will have less stiffness. So as example of material that would be less difficult or more stiff, you might start off with something like rubber. Okay, where you get a lot of stress strain for a very little stress. You will get if you give a little stress on the rubber, you will get lot of strain. So that's got low stiffness. Okay, so rubber has low stiffness. Rubber, so rubber has low stiffness. If you give the small stress, it will get stretched out and it will get long straight. So it will be kind of this rubber. Your slope will be less, so it will be less steep. Okay. So you can take human bone or cartilage would be maybe a little bit steep, a little bit higher stiffness, and then maybe concrete. And then can you get into your metals like aluminium, copper, and steel have more stiffness. Okay, rubber. Suppose rubber. I'm taking a rubber, then human bone. It will like this. Suppose it has a curve of this. Then you can take aluminium, alloy, copper, metal, steel. It will have like this. So which one will be stiff? So the curve which has more slope, that will be more stiff. And finally, the stiffest material you can take as an example of diamond. It curves like will be like this, I guess. Complete. So it will have more slope. So it will be the stiffest one. If I need to compare these four graphs and I ask you which one is more stiffer, then you have to see the slope, and you can directly say that this one will be more stiffer as it will have more slope. So hope this part is clear. The stiffness. Okay. So then we'll move to the next property, which is strength. So how you will give the strength of the material? It will be the capacity of our high stress where the material has its ultimate stress or ultimate, what we also call ultimate strain. And the strong material would be something like nanotubes, a lot of ultimate stress that it can take, and so capacity for high stress or ultimate stress will go with strength. Where is my note? So for the strength property, you see capacity for high ultimate stress. So where we got ultimate stress? This point, right? At this point, we'll got high ultimate stress. So this will represent our stress. Suppose a similar curve has, suppose a similar another curve. Let me note once again. Suppose a curve has, this is its ultimate stress. Okay. Which one has higher ultimate stress? This one, comparison to this one. So it will have more strength than this curve. This curve, understood? Suppose this is a curve of rubber, suppose steel, and this is a curve of rubber. So rubber has ultimate stress at this point. So this is the ultimate stress of rubber, and this point is the ultimate stress of steel. So which one will be more strength? So your more strength will be, this value will be your for steel, not rubber, because rubber has less ultimate stress than ultimate stress than steel. Clear this part? Hope this part is clear. Next we'll talk about toughness. Next we'll talk about the property which is toughness. Okay. Now this toughness is capacity for energy absorption. How much energy a material can absorb. And from the stress strain curve, the toughness is calculated or can be known as area under stress strain curve. Now whatever be the area under this curve, it will depict your toughness. Clear? An example of this might be, you can take as guard rail, where you want it to deflect a lot, take a lot of stress and take out the energy, or maybe a barrier at a tool booth. Okay, you can take. So suppose this is one is curve, it has area under this curve as this much. Suppose you have another curve that will have area much more than this. So which one will be more toughness? The curve which has more area in the curve which has more area in this area under this stress strain curve. Understood? Toughness. Now resilience. See, go with this words, okay? Property of the word resilience. Resilience is capacity for deforming elastically. So how much it can bounce back? How much it can bounce back? It will define the resilience. If we stretch out how easily it can deform, elastically deform. It bounce back. Okay. So for this property, you will compare area under elastic region. So this is the elastic region. Suppose okay, this is the elastic region. You have to find the area under this curve. Suppose another curve you have to find the area under that region also and compare which one will have more resilience. The more the area, more will be the resilience. Next, come to the ductility. So ductility is nothing but how capacity for height, deformation and strain. Up to what capacity it can deform. Okay, and from stress strain curve we can see that more the deformation area. This is the deformation area. Some curve might end at this point. Okay, some curve might at this point. Some curve might at this point. So the curve which has more area, stress strain curve area, more deformation, more strain area. This is the strain part, strain area that will have more ductility. And ductility, a lot of metals are very ductile. Thinking like if we take steel, aluminium, copper, maybe lead, brass, bronze, those are all ductile materials. And then we call, okay, those are all ductile materials. That means for ductile materials, when the curve becomes very long, more the curve, more will be the ductility of that material will be more. If this I told you this curve is more for, suppose I'm taking a rubber and this is taking a, suppose another any material, XYZ material. So this has this much area. So more the area, stress strain curve, more will be the ductile. Okay. Then we can go for brittleness. Okay. One that has very low capacity for deformation or strain. So as we go up, we get into plastic region. It fractures a lot quicker than a ductile material would do. Okay, it will. Students are coming now also. So it will have low capacity for deformation and strain. So that will come under brittleness. You can take an example of glass. Okay, cast iron, ceramics. So those are some typical material. These are the some typical material properties we have discussed. Number one, stiffness, strength, toughness, resilience, ductility, brittleness. Okay, and if you have been asked to find these properties from a curve, you have to consider these points. Okay, for stiffness, you have to find the E value and compare, and for strength, you have to take the ultimate stress. Toughness, you have to consider the area under stress strain curve. For the resilience, you have to take area under elastic region. For ductility, you have to take the how longer the material this curve under for capacity for high deformation and strain. More the longer the curve, more will be the ductile, and lower the curve, it will be more brittle. So this is the worksheet I want you all to do. Okay, here different stress values are given to you. Okay, and there you have three typical material properties. Three different typical properties. One is steel. Don't get confused with A36 standard structure alloy. Don't get confused with these words. Just consider one you have. These are the name for the namesake. Okay, but the actual is steel. You have steel, you have aluminium, you have magnesium. So these are three stress strain curves given to you of different material: steel, aluminium and magnesium. Here different strain values are given to you. Here different stress values are given to you. What you have to do, you have to find these Okay, you have to find modulus of elasticity of steel. For the steel curve, which one is steel curve? This one is steel curve. You have to find the modulus of elasticity, E value. Again, you have to find ultimate strength for steel. Ultimate strength for steel. This steel. For this steel, you have to find an ultimate strength. In the same way, next question you have to find ultimate strength for aluminium. Then you have to find proportionally limit for magnesium. Yield stress for 36 steel. Then it is asked to you that which material will be strongest, aluminium or magnesium. Which one will be most ductile among these three? Which will be most brittle among these three? And which will be most stiffer along this three, and with a reason. So please draw this curve. Please draw this curve in your copy. Draw this curve in your copy. Plot these values and try to do the try to solve this curve. We'll soon discuss the solution also. Am I audible? Note down this question in your copy and first draw this diagram. Then we'll move to the question. Draw this diagram fast. Am I audible? Hello? Okay. Okay. Draw this
Yes, ma'am.
draw this curve in your copy. Quickly. Draw this curve in your curve. You have been given a 3 curve. Okay. You are given a curve of steel. You have been given a curve of S-testrin, curve of aluminium alloy, and then magnesium alloy. So, hope all of you have drawn.
No, ma'am.
Okay, do it. Or you can directly draw this one. It will become easy for you to answer the questions. Draw this one. The same curve, just the dotted lines are here. Why these dotted lines are here, you will understand in a minute. Done? All of you drawn the figure? Shall I move? Please respond.
Yes, ma'am.
Okay. What about other students? Write yes or no. 48 students, only one is replying to me. 47. Why? No, ma'am. Please draw. Okay, with majority I'm going. Okay, with majority I'm going. Okay, so see. Okay, just see this figure. Okay, I have to discuss some more topics also. ma'am. No, ma'am. Yes, ma'am. Okay. Okay. I have to discuss some more topics as well, so I'll won't wait. I'll continue. Okay. So see, what was the first question? Oh shit. Sorry. Okay. So first question was approximate modulus of elasticity. Ma'am, roll number 8 got disconnected and is not able to join now. Leave it that part. Let's focus on the class. What is the approximate modulus of elasticity for A36 steel? So you have to found out what is the modulus of elasticity for the steel curve, right? So which one is your steel? This one was your steel, and you have to find the elasticity, modulus of elasticity. So what is the formula for modulus of elasticity? This is stress equals to Young's modulus and strain, right? And you have to find the Young's modulus. So what it will be? Stress by strain or not, right? So what is the stress value for this curve? This is the steel curve. What is the at this point? This is the elastic region. You have to find the slope at this point. So what is the stress in this region? It is 250. So write 250 here. And what is the strain at this point? How much it will be? It will be 0.00125. If you plot this curve in the graph, then you will get this value. Okay, write this 250 by 0.00125. How much will be the Young's modulus? Tell me fast. Always sit, pen, paper, your notes copy, and with calculator. What will be the E value now? Tell me. Respond. What will be the E value?
2 lakhs, ma'am.
2 lakhs. Anyone? 250 divided by your 0.00125. What will be the unit?
No unit, ma'am.
No unit. How come? How come? No unit. See, your stress has unit of how much? Your strain doesn't have any unit, right? But your stress has unit. So E will have your unit. Your Young's modulus have unit. See, the stress has unit of how much here? MPa, right? MPa. But your strain doesn't have any unit. Here it is written mm per mm. So it will get cancelled out and it doesn't have any unit. Okay. So your elasticity modulus will have the same unit with your stress. Whatever be the unit of stress, that will be the unit of E. Understood? So your value will be 2 lakh MPa. Next, what you have been asked to find out? Ultimate strength of A36. Now, if you go back to this, ultimate strength will be nothing but your ultimate stress value. So what is the stress value for steel? It is 400 MPa, right? Yes or no? You have been asked to find the ultimate strength of A36 steel. Ultimate strength will be represented by a ultimate stress. You go by this. Ultimate, your strength will be capacity of high stress or ultimate stress. So your ultimate strength for A36 will be 400. Next question, ultimate stress of 6061 T6 aluminium. Means you have been asked to find out the ultimate strength of aluminium. So this one was curve of aluminium. What was its ultimate strength? If you mark this point, this is 310. 310 MPa will be your ultimate strength of this aluminium. Okay. So this is the answer. See, E equals to stress by strain 250 by this 2 lakh MPa, or you can also convert into GPa. Okay, 1 MPa will be 1000 GPa, so it will convert it into 200 GPa. Next, ultimate strength of A36 steel, what we found? 400. So it is 400 MPa. Ultimate strength of aluminium we have found 310 MPa. So this is 310 MPa. Now they have asked you to find out approximate promotional limit of magnesium alloy. proportional limit for magnesium alloy. So how to find out the proportional limit? This curve, the point where the curve starts, means the straight part of the curves get deformed, that is your proportional limit, right? So for this curve, they have asked to find out the proportional limit of magnesium. So for this magnesium, when the shape gets deformed from this point or this point, if you straight it down, this is, so 125 MPa is your proportional limit. Got it? Now they have asked you to find the yield stress of A36 steel. What is yield stress? The next point, right? So this is your, for the next point, yield stress of A36 steel. So A36 steel is this one. This is your yield stress 250. So same, it will be 250. Okay. Now they have asked you to find which material will be strongest. So which will be the strongest? Which will be the strongest? Tell me from the graph.
Aluminium.
You have seen the answer, right? Aluminium. Why? Because it has more area than magnesium. Okay, this part. Then you have to find which one is ductile. Ductile will be magnesium, because see, magnesium has longer area, longer curve, right? From comparison this and this area, magnesium has longer area, so it will have, magnesium will be more ductile. Then they have asked you most brittle. Aluminium is the shortest curve, so it will be most brittle. Then they have asked you which material is stiffer. So just see the curve, from the curve, this part is more stiffer, so it will have more E value. And which will be the least stiff? Understood or not? Which will be more stiff? See, E value from these three curves, this curve has more E value comparison to this and this. So most stiff curve will be of steel and less stiff will be of magnesium. Clear? Hope this part is clear. Write down the answer very fast. Write down the answer so you can take a photo and later on write it. Clear with this part? Response, people. Okay. Thank you for responding. So, till now, what we have discussed the strain curve for different materials. Okay. We have discussed the different stress strain material for different curves, different material, aluminium, steel, magnesium, right? Again, as I have mentioned before, it is typically used for all this steel, aluminium, magnesium, all these used in our day-to-day life. Okay, in machine parts, shaft, different purposes we need this type of material. That's why we need to study the material behavior of. That's why we need to study this subject actually. What will be the mechanics? How this material will behave? Okay. Aluminium. Okay. Basically, steel is used in your machines parts. Okay, and your aluminium is basically used in the past of for aircraft frames. Okay, although we are not seeing a lot more of composites nowadays because of aluminium, but it is used to. The strength to weight ratio in aluminum is better than steel. Although steel is stronger, but the strength to weight ratio of the aluminum is better. That's why in most of the thing, aircraft frames is being used to make in aircraft frames, or all are used to make by aluminum. Okay, so the strength to weight ratio is the reason they use in aircraft, because you can get a lot of strength for less weight. That's what you want to have in an aircraft type application. And you are starting actually to see aluminium used in cars and pickups these days. Next, what we see, the third material in the stress strain curve is magnesium. Magnesium is a low density material, about two-third of that aluminium. Okay, it has good corrosion resistance. It has good high temperature properties, and it is used in electronic applications and some other specialty applications. So here is the stress strain diagram for three typical materials. We have talked a lot about steel, where we have pretty well defined yield points, where we start to get plastic yielding, and some materials like aluminium and magnesium doesn't have well defined yield points. See, if you see this steel curve, let me note. If you see the steel curve, you have well defined yield point, right? But in magnesium, you doesn't have a perfect yield point, and in aluminum and magnesium, you doesn't have a perfect yield point. But in steel, you have perfect yield point. This is the straight part. Now from here, it is moving. So what we do when we doesn't have a perfect yield point? Let me admit, the students are coming. So what we do when we doesn't have a perfect yield point? So you can see from the diagram itself, steel has a perfect yield point, and these two material doesn't have a perfect yield point. Okay, you have to zoom it sometimes. So what we do when we doesn't have a perfect yield point? And what is the yield stress? Material without an obvious yield point. What we do? First, let's discuss the yield stress. So what is the, we got yield stress, right? Earlier we got the yield stress. This is the yield stress point. This is the point where the deformation starts. Okay. Lowest stress that produce permanent deformation. From this is the lowest stress. One we have ultimate stress, one we have yield stress. So this is the point from where your deformation starts, or you can say lowest stress that produce permanent deformation. From this point you will get a permanent deformation in the structure. So if you doesn't have a perfect yielding point on a curve, so it is difficult for us to identify where is the yielding point on this curve. So what we have been asked, or we can do, if the point of yielding is difficult to identify, typically the 0.2% offset yield stress is defined. Suppose this is one curve. Let me note. Suppose this is one curve. Picture visibility is bit low. This is nothing. This suppose this one is I have one curve till here proportional limit. That means your curve is straight, or you can say this is the linear region where till this point your stress is directly proportional to strain. After this point, this is not gonna happen. This is the actually beginning of non-linear part, but you are not understanding where to start, which will be the yield point. So what you have to do, you have to take 0.2% offset of yield stress. If you take a offset of this point, here you have to take 0.2%, 0.2% of the yield stress. That will be your yield stress value. This 0.2% of the strain, for this 0.2% of the strain, if you draw a line, this point will be your offset yield stress. Understood? Why we are taking the 0.2 from this curve? What suppose I am taking here 0.2% strain. If I draw a straight line, if I draw curve to if I draw a line to this curve, suppose this is intersecting this point. So along with this point, whatever be the stress, that will be my yield stress, offset yield stress. Okay. Here I have been here. This is perfectly visible. Suppose this curve I am not getting which one to take yield stress, right? This will be more in clear in this line. This line. See, they have just simply they have what they have taken. This is 0.01. Na? They have considered a 0.02%. Mark the straight line here. They have taken an offset of this. Let me note. Let me note. Let me note. Okay. So I have taken, see, the yield stress is not visible to this curve. What they have taken? They have taken 0.02 offset. This, suppose from here to here, this is the 0.2 point. I have marked. Just wait a second. Okay. So suppose 0. This is my 0.01. Suppose my 0.02 point is coming here. I have drawn a point here. Okay, I have taken out the point in this curve. So corresponding to this point will be my yield stress. Corresponding to this point will be my yield stress. So 125 is my yield stress. So what they have taken? They have taken 0.2% of that. When your yield stress is not defined, you have to take this. You have to take 0.2% offset yield stress. Understood? You have to take in 0.2%, draw the curve to draw a line to that curve. Then corresponding to that point will be your offset yield stress. Hope this part is clear. So this is another question. Draw the figure. I'm not gonna explain this. You find out by yourself. What is the approximate 0.2% offset yield stress of aluminium? You have to find the 0.2% offset yield stress of the aluminium from this diagram. Draw this. Write down the question. No need to draw the steel and magnesium. Just draw the aluminium curve. Okay, just draw the aluminium curve. Or you can take a screenshot. Okay, you have to find, for this question you have to, what you have to do, you have to find the approximate 0.2% of yield stress of aluminium curve. This is the figure. Shall I stop sharing? Please respond, then I'll take the attendance. Shall I stop sharing, or you need time to take the screenshot of the. Okay. So all of you write your roll number in the chat box. Any confusion till now from today's class? Any confusion? Many one of you left the meeting, then again joined the meeting. Hope the now rating system is clear to you. How to rate the class, how to attend the class, how to how to see the videos of the class. Hope everyone is not finding any issue with that. Everyone wrote their roll number? 48 participants. Someone wrote about some student joined the class. Roll number 88 got disconnected. Okay, you can. I'll stop recording the class. You can leave the